Congratulations, you made it to Monday. It's a nice day outside, so get your work done or as much as you can. Go outside, take a little bit of a break and enjoy it. This is definitely weather we're not going to see lasting much longer here. So it's 9:30 in the morning. Page 1. All right, so we're near the end of it, guys. So here's what's on the old agenda. Quiz 10. Probably should 10 quizzes at least, and 10 quizzes looks like what you're going to get. It looks like it's available. We'll see. It's been a while since we had a quiz, but do 36 hours from when it came online. It came online early this morning at 6 a.m. But I don't think you're going to need 36 hours to do it. So, somebody in the waiting room. Who's in the waiting room? There we go. Okay. And I also said we had probably about 10 homeworks, and why not? 10 homeworks due by Thursday, November 13th or November 12th. We want to avoid Friday the 13th, right? For suffering from triskaidekaphobia. I think that's fear of 13 or the Friday the 13th by 6 p.m. And of course, we'll be lecturing all through the week. And then we'll lecture on Monday as well next week. And then after that, that's it. As far as lectures go, we just finished off with some fun stuff. Wednesday, November 18th. That's exam number 3. Format to be determined. It will probably have a little bit difference than last time, but I'll talk about that later. We get a little closer. Where it's going to be, it won't be anything new you haven't seen, just a little bit on how it's structured. November 20th, a week from Friday, is our last regularly scheduled meeting time. That's for the makeup exams. And then we have a weekend. And you should have got this email this weekend from me. I finally found out about it. We have been okay for a final. And that's from 9 to 10:50 in the morning for everybody. All right, so it doesn't matter what class you're in, that's everybody.
Is it going to be online?
It will all be online. It's either virtual, not in classroom, or by PC, still online, in classroom. So now I don't know what room we'll be in. We'll be in a room in Smith Hall, 2nd floor of Smith Hall. So we'll be up here. If we're lucky, we're in this room. If not, we're not. And this goes for all sections. We'll just stuff as many people as we can. I don't anticipate the survey that came back, that one that was for the bonus. Only one person indicated they'd like to be face to face. Overwhelmingly, not everybody responded, but I don't know. 20 more people said no. It'll be the same time, same date. Everybody's going to take the exam at the same time. You can either be like we have been in your room or wherever you're at, whatever continent you're on at this time. This is, of course, Eastern Standard Time on this date, or if you want to, you can be in this classroom and you can be with me. What the positive about being in the classroom is, if you got a problem, you can raise your hand like the old days, and I can come get you fast. You know, I don't understand what that angle is, or you're missing the angle, or I don't understand what this is showing me. Well, I can't tell you everything, but obviously it's a test. But you know, if there's some confusion about you don't understand what I'm asking for, I can, hey, on this one I'm asking for. That's the mass, whatever. Blah, blah, blah. And the big thing is some of the final will be a hybrid final. It'll look like kind of like exam 1. A lot of you didn't like that multiple choice, but exam 1 had multiple choice on it. So it'll be some multiple choice like And I say multiple choice like, what's that mean? Well, there is an option I can have like drop down boxes, or I can have fill in the blanks. Depends on how much time I got for Canvas to work with that. So that's a little bit nicer if you got fill in the blanks, because then you can put your answer in there instead of having to find my answer. Of course, still, if it's really wrong, it's still wrong. But maybe anyway, there's pluses and minuses for that I've looked into, and I'm still trying to figure out how I'm going to do it. But also definitely, and some show your work. Problems. So there was partial credit possibilities. But the problem we encountered with exam 1 was Gradescope got a little finicky. Sometimes your connection would crash. Sometimes you wouldn't upload the entire picture, and that was just too late. So I thought maybe if we had it in class, you would be working on your PC. But when it came to this part of the problem, when it came to like, oh, here, I've done the long problem, I'm done with it. Snap, here, Professor Brown, here's my problems, and that's it. Okay. That prevents the possibility of a computer problem, or an inadequate picture, or a fuzzy picture, or a dark picture, and I can't read your work. And once you submit, that's what we got. Right? So I thought maybe I'd try that. And also, I can be here for questions if you want to. And of course, I'll be live like before. So if someone asks a question in the room, it'll be transferred to everybody else online. Oh, there's been a question about figure 3, blah, blah, blah. Here's what I'm talking about. So you won't get any additional information, just a little faster, and you can point to things. I know it's been I think you realize it's been kind of a trying semester for us all, but it's so hard to do the most basic things now. These problems we do in class, I'll do them, and you'll be we're going to work on a couple in just a few seconds here. And all the answers 100, you'll come back and I'll hear this voice. I got 21. And I don't know how you got 21. In the old days, I'd look over your shoulder and okay, I can see you got your angle wrong, or you got a force drawn wrong, or you forgot to divide by 10, blah, blah, blah. But and sometimes it's not always that easy to do, but it's the way you got to describe this. Something discussing. It's almost like trying to do physics via radio. Anyway, all right, so we're going to start today by doing problems. Let's see what we got, you guys. Problems number 5 and number 8 on the spring. I forgot what I exactly called it. I can look up pretty fast, but spring power worksheet. For those of you online, I've got it printed out for anybody here in the room. But for those of you guys online, go down to Canvas, and I've had a lot of stuff. I've had the lectures and PowerPoint. Just kind of start at the bottom and start working your way up. And there should be one. Find it fast. Why am I even acting like this is mystical to me? I can just find it. Let's see. Blah, 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 blah. Zoom. Let's go here. Let's go here. Class. And so if you want to know what exactly it's called, according to my screen, it is the 4th guy from the bottom of your Chapter 7 Work Energy module. And it says 11/06/20. That was the date we were going to hopefully work on, because it turned out that it was the day I just entered it. Springs and power worksheet. So that's what it was called. So download that puppy and do problems number 5 and 8. You can work on the other ones you want, but I'm going to give you about 10 minutes. Then we'll discuss them. The other class did 4, 6, and 7. 6 and 7 are related. And oh, by the way, before I do that, I forget that. There was a typo, my bad. That's the worksheet we're going to be dealing with. Some folks asked for a few more work kinetic energy theorem problems, so I threw those on there just for the fun of it. No more extra problems with it. We're going to jump in here with. We're going to jump in here with good old number 5, but there was a typo. Okay. I'm going to get you guys in. 6, which is okay because if you listen to the lecture, I'm going to take all the video lectures. I'm just going to. This was the great plan. I actually want to get figured out after I made them, but hey. We'll do a few problems in this class, a few problems in the other classes, and hopefully there'll be different ones that are scheduled. And I'm gonna cobble up the video. So when you look at the video, you can see all the problems being done, or most of them. I said, you guys are doing that one, and you're doing number 8. All right, well, let's do these guys. Page 3. All right, so we have a cart sliding horizontally, and it's going to run into 2 springs. One spring, it's going to hit first. This is the K1 equals 1600 Newton meters. And then we got the second spring over here. It's going to compress this guy 0.3 meters, and it keeps on going, then compressing both springs, an additional 0.2 meters for the first spring, and it's only 0.2 meters going to be compressing the second spring, whereas spring constant is 3,400 Newton per meters. We're asking, the cart is brought to rest at this spot, so what was the initial speed of the cart? All right, now this would be a problem we can do maybe with some, this would be tough actually with Newton's second law. We can do it, we didn't do anything with that. We dealt with constant forces. Now this force is not constant. We have springs here and they're non-constant force. So what do? Well, you may be limited in what you can figure out, but we can actually figure out a lot of valuable stuff, including our initial speeds of this cart. And how we do that is we use the work kinetic energy theorem. And this states that the net work done on an object will result in a change in its kinetic energy. You apply you do positive work on a soccer ball, you kick it, it will zip away from you. It will speed off. It starts at rest and will accelerate and go to the final speed. In this case, if we have a cart moving along in a certain clip, which we don't know what that is, here's what the answer is going to be. We don't know what it is. Pi equals I don't know. Eventually, it's going to run in these springs, and the springs will stop it. So the work done by the springs is going to be the what will cause a change in kinetic energy for our cart. So we talk about work done by spring 1 plus the work done by spring 2 equals 1/2 mv final squared minus 1/2 mv initial squared. No, that's what delta K is. So this is like a placeholder theorem. Right off the bat, I want to probably just slip it down here, maybe unless I'm just trying to figure out final K or kinetic energy or initial kinetic energy, which is something you can do, but it doesn't say much. But these we'd like to get usually. That's something we'd like to find. If you look at other forces which are acting in a cart, you might think, how about the normal force? What about the gravitational force? Well, we've gone through this several times already. Yes, they're there, but the normal force points perpendicularly up. The gravitational force is perpendicularly down. Your displacement is going to the right. So the work done by either one of those forces is 0 because the angle for this between the displacement vector, an arrow to the right, and either one of those two forces, which are perpendicular to the horizontal, is going to be 90 degrees. Cosine 90 is 0. So those guys here are present, but they just give you no work. So these are the guys which are going to do it for us. I mean, that's why the cart just keeps on going until it hits the springs. Nothing's doing work on it to slow it down until it hits the springs. We have to assume there's no friction. Wait until Wednesday, we'll be able to deal with friction then. Okay, but right now, work kinetic energy theorem. I mean, we could actually deal with that. If there was friction present, we'd have to add a term here, work done by the frictional force, but we'd have to have a lot of other information given. We have to know the mu. We'd have to know how far this cart is traveling, because the work done by the frictional force depends upon the distance traveled, as any work equation does. So that's why the easy option, just to show us the springs in action, was to say there's no friction, we just work with springs. So you look at the book, and we were looking at our notes, and we talked about two different equations for work done by the springs or work done on the spring by an external force. The guys which are actually slowing down the cart are the springs, so you've picked the spring work equation, so it's negative K1 over 2. And in the notes, and the book does too, it writes this XB, XA, but it's a new week, and I just like to hit home that these X's are, remember, are stretches or compressions from equilibrium. So this would be X final 1 squared minus delta X initial 1 squared. So maybe it's easier to see it this way. Maybe it's not, but remember these guys is how far from equilibrium. What we call an X naught.
What are all those little subscripts after the F?
After this,
Yeah.
that's a comma 1. If
Okay.
you want to just write F1, I don't, may that be easier. And I1, sorry. And that's just for spring 1. And you know why I got to put the 1s here, because here comes work done by second spring. And he's got his own K. And these springs are being compressed a different amount. One guy's being compressed a lot, this little thin guy, and the other guy's not getting compressed as much. So we have potential for different delta X's or your stretch or compression. So this would be the final compression for spring 2 squared minus the initial compression, for spring 2 squared equals, kind of running out of room here, but I can save myself a little trouble. The final speed of my object is 0, comes to rest. So because it comes to rest, I'm just left with a negative 1/2 mv initial squared. The initial deltas are how far the springs are initially stretched or compressed before this cart's going to come to it. And they're just standing out here waiting and oblivious of what's about ready to happen to them. And as any good spring will do, if nothing's acting on it, like a cart or a person, then these guys are at their natural length. There's nothing keeping these springs compressed or stretched. So initially, these guys are just zeros. And at the end, though, spring 1 is going to be compressed a certain distance, 0.3 plus the 0.2 meters, and spring 2 is just going to get compressed by 2 meters. Sorry, 0.2 meters. So we can plug in our numbers here. 1600 over 2 times the 0.30 plus the 0.20. That's the total stretch, sorry, total compression of spring number 1. Minus 3,400 over 2. And he only gets compressed 0.2 meters. Equals negative 1/2. 6,000 is its mass, v initial squared. So now you're at the mercy of algebra. See if I can do it. See, 0.5 squared, 1600 plus solve this for VI, and you get the answer that we should get, 0.299 meters per second. Or we just want to round to 0.3, go for it. It's just solving for VI. The question is in the class, how'd you get this number? It's just, let's just solve this equation for VI. I mean, What, the first term?
Is the net worth 353 joules?
No, I think it's like negative 268. This guy here equals negative 200, and this one here equals 68. Negative 68. There you go.
Oh, okay.
There you go. Of course, all your negative signs are going to cancel because there's a negative sign in front of every term, so they cancel out. Just add them if you like. But definitely don't subtract out one from another positive. They're all negative. They're all positives. Of course, at the end, the negatives will cancel. So let's get that guy. All right. So if you're okay with that, I mean, it's just algebra. If you're okay with this, the key thing is to get to this step right here. If you're okay with that, then this just falls out. All right. So number.
How'd you get to the 229 again? Because I had the answers for the first two things and I had equals and then negative 5.
Like that for
So how do you get
Just algebra. I mean, it just, did you get the negative 268?
Yeah.
Just divide that by, just make it, okay, so is it still negative 268 in your calculator?
Yeah.
Divide by negative 3,000. That's this part right here. That'll get rid of
Give
it.
me 0.089.
It's possible. 0.089? You took 268 divided by 3,000. Let's see. Oh yeah, there you go. That's right. That's 0.089, and then just take the square root of that because you got v initial squared. So I take it, yeah. And when you take the square root of that guy, then you'll pop out the good old 0.299. So it's just you get set up. That's great. That's the key part. All right. No other question about that guy? Yeah, it's algebra to get this on that one. All right, so the other one we do, commercial claims. I did this in the other classes on Friday, but so I left it for you guys. Well, I didn't mean to leave it, but when I did, I thought, yeah, that's great. I'll stick it in here. So a commercial claims that a car, no mass, can accelerate from rest to a speed of 25 meters per second in a time of 8 seconds. What average power is produced by the motor to produce this acceleration? Disregard frictional losses. Yes. What power equals work over delta T? Also equals the amount of energy change, but we got work here. And this would be your, we're looking at the motor, but the motor, you can talk about the net power done, or net power in effect, and that's done by the net work done on an object, or delta T. There are no other forces acting on this car except for the motor. It's not very good to disregard frictional losses. We're just showing an example here. If we wanted to do frictional losses, we can easily add that in there. Okay, so but for network, it's just going to be the work done by the motor over delta T. And so what do we know about the work done by the motor? Well, we just had the good old kinetic energy theorem, but work net equals delta K. So I can plug in here 1/2 mv final squared minus 1/2 mv initial squared over delta T equals P of the net, which is going to be P of my motor. And the reason this is true is because the motor is the only thing acting on my object. Nothing else is working on it, so the power is just the power of the motor. The car starts from rest this time, unlike the last problem where it ended up at rest, so it's going to initial 0. The power by the motor is 1/2 m. That's your master accelerator. That's the car. Times v final, which is 25. Don't forget to square it. All this over 8 seconds. And that comes out to be, if we round it to the 100 spot, 46,900 watts. That's it. That's a just general power equation. So remember, work we can always do with force D, delta R, cosine theta, or if we want to, we can do the work kinetic energy theorem. And you think, oh, which one do I do? If you start seeing things like, initial speed given, final speed given, starts at rest, it's initial speed 0, final speed 25. Yeah. Boy, I'm probably going to deal with some kind of work or energy here. I'd be thinking maybe work kinetic energy theorem. And that'll give me my answer. Otherwise, say, well, I don't know that. How about if I can just use the work equals force times distance times cosine theta? Sure, you're more than welcome to. And when you start doing that, and it's a great thing to do. And when you start looking at it, you think, wait a minute, I don't have anything about distance. I don't know that. I don't know anything about a force either. I just here's the mass. And maybe if I can figure out the acceleration due to the one equation of motion, yeah, sure, give it a shot. And using Newton's second law, F equals ma, I can get the force. That's true. And may it all work out. But and that's true. Maybe that's it. But I would just think, is there any other way I can do this? And if you look, there's not many other equations we got, but we had the work equals kinetic energy theorem. And I think, hey, you know what? That's kind of ringing a bell. Maybe I can use that. And sure enough, it pops right out really fast. Right? Otherwise, so it's a lot longer problem. A really lot longer problem. You got to do a 1D motion problem. You got to do Newton's laws on it. And then finally, you get F net. And if you're still going, you can get your answer. So that's problem number, that was our second one. Like I said, the goal will be, or my big vision is, I'll have this online with all the, well, I'll have the PDF version with all the solutions on it. And then I'll have the video with just me cobbled it in there with, so you may have a change in background noise when suddenly, suddenly I'm doing problem number 6 and 7. And that's because that was the 8 o'clock class and they did different spring equation than you guys, and the 11 o'clock guys are going to do the other one. So that's the so, just bring up here. And this is its natural length. Now this is a vertical spring. We did X's for horizontal springs on Friday, but I don't think it's a big stretch for us. No pun intended with springs. It's a vertical, guys, so we'll just make all our X's and the Y's. If you'd like to keep them all X's, you're fine. It's kind of looks weird to have a vertical spring. We'll never have a combination X and Y. So we have this spring and we add a little mass to it. Let's call that M1. Okay. And when we have M1 here, it stretches it a delta Y. Right? A delta Y, I don't know. It just says it stretches it from equilibrium. When I add more weight to it, M1 plus 0.02, I find out that the thing stretches a delta Y of 0.07. So in other words, adding this mass, not M1, just adding the additional 0.02 kilograms, causes it to stretch that distance, 0.07 meters. So Hooke's law is just K delta Y for just the magnitudes. Okay, so I don't care about which way it's pointing, I just care it's just the magnitude. What causes the spring to stretch? Well, the spring won't do it, but there's going to be some other force which is doing it, and that's just going to be your weight. It's the weight of the additional force, sorry, the additional mass of 0.020 kilograms causes an additional stretch of 0.07 meters. So force equals mg. I'm going to substitute that in for here. That's because if the spring force is equivalent to this guy, that's why it stops moving. The spring force is trying to pull him back up. The weight's trying to pull him down. The mass will stop right here. There's no acceleration on it, and let's go back to Newton's second law of the force tables, or force diagrams, as my wife says I should start calling them. And that's because the acceleration is 0. Those two forces are equal but opposite. So since I'm just dealing with the magnitudes, I'm just going to stick in mg there. Equals k delta y. K equals the mass that I added divided by the stretch what happened because of that new mass being added. And we do that. I guess I should have a calculator. It's the time you grab a calculator. 2.8. Now this is the meters per second squared. That's in kilograms, that's in meters. Oh, what's that going to be? Well, you can do it with unit analysis. It would be the best. We don't have time for that. I'm hoping, fingers crossed, that my units will be in newtons per meter because all my units were in standard metric units. Meters, seconds, kilograms. And that's how you do that, guy. And the other ones you're going to find out, you actually know an initial and final. So, and just the way it's worded, it kind of points you towards using the work theorem for springs.
Professor,
Yes.
why do we use for mass, the 0.02 and not 0.05?
Because the distance that we're given, this is the distance. This is the distance that the spring stretches because we added that guy, 0.02. This stretch came from adding him.
Okay, so we just don't have to use that 0.05 at all.
That's right. He's a red herring up there. Be careful about him. Initially, I thought about maybe doing a two-part problem. I just scrapped it or something like that. It all made sense at the time. And I just left it. I just made a simpler problem. So sorry, the simpler problem got it harder, actually. Actually, sometimes it works out that way. Don't mean it to be that way. But always be careful when you're working with anything. Make sure, and this goes all the way back to the projectile motion. That this time corresponds to this delta x, which corresponds to this delta y, or vice versa. We had to make sure that when we went from back and forth between those scorecards, we had to make sure everything was describing the same situation. All right, any other question about that guy? Okay. All right, the other guy, the longer one, maybe the more straightforward one. Maybe it's longer, but it's at least easier to see. Yeah, it makes sense. I got a little snag there, but I see where I can keep, where I stumbled. I keep going now. We have a block sliding down a surface, an incline. And there's a frictional force present. We'd like to find the power that the frictional force generates on the block when the speed is 3 meters per second. So it's going to be accelerating down the incline. And at the time, 3 meters per second is the speed of the block. Well, how much power is the frictional force eating up? So there's a 30-degree angle. As far as our block goes, direction of motion. And what's bringing it down is the weight. The weight's bringing this thing down. And the other force we have a normal force and the frictional force. All right. So what do we want? We want power, and specifically power by the frictional force equals work done by the frictional force over delta T. That's the basic equation for power. And this can also be delta E, energy expended, but okay, we're still kind of dealing with work here most of the time, but we're segueing into, or transitioning, it's a fair way I can say it on a Monday morning, into the energy concepts. Well, I look up here, I don't see anything with work. How do I get work? Well, work, I have an equation for work. Provided the force is constant, the frictional force would be constant here. It's just going to be your force, frictional force, times your distance traveled, times the angle between the frictional force and this delta R over delta T. So if we look at the frictional force in the direction of travel, this is your direction of delta R. Delta R tells you the direction you're moving. What's the angle between the frictional force and this delta R? 30? Between the frictional force and delta R. 180. There you go, 180. So it's 180. Frictional force goes here. Delta R goes there. So theta F equals 180. Okay. So we're just looking for the frictional force, and I might as well, combine a few steps here. One thing, I don't see a frictional force mentioned up here. Well, I see it mentioned, but I don't see it given. So what do you do if the frictional force isn't given? How do you find it?
The normal force multiplied by the constant of kinetic, or the
There
friction.
you go. Yeah, I got it. It's stretcher. So I was stretching, so I didn't catch it, but you guys got it for me. Yeah, it's the friction equation, which is going to be mu Fn times delta R cosine 180 over delta T. So now we can, cosine 180, we know it's -1. The normal force we can get, so let's call this P of friction. Let's leave it as A, even though I have one big clear. I'm having problems trying to get that normal force. So I need a normal force. So you go back to good old Newton's second law. That equals mg. That equals 30. Here's your normal force. Well, your normal force. Uh-oh, that's joined. It's terrible. This was exam 2. So this was the punchline for exam 2 to find like a normal force and a frictional force. Now it's just like, okay, if you want to do work, sometimes you got to go back to Newton's second law as a side note now, and get whatever information you need, including in this case the normal force. So normal force minus mg, not quite, mg cosine 30 equals 0. Normal force equals mg cosine 30. So plug in the A. Just using that piece of paper probably, but I like to keep it all here so I keep pointing back to it. If you have trouble, you can always look at the video and see where all these numbers are popping in at in what order. So the power equals mu. Here comes the normal force, mg cosine 30 times my delta R times -1, that's cosine 180 over delta T. But anybody know what delta R over delta T is better known as? Change in location, change in position over change in time. Yeah, meters per second. That's just speed. Equals mu mg cosine 30 -1 times v. Delta R delta T is just v. It's just your speed. And your speed's gonna be changing as you go down the incline, which means the power that the friction is gonna be lopping up, it's gonna be increasing, which kind of makes sense. If this was rough enough and it went on long enough, ooh, it'd be getting hotter and hotter and hotter due to that frictional force stealing energy away. But anyway, we've got to the equation now we can actually use. Let's plug in our numbers. 0.25 times 5 kilograms. Keep some units in there so we can see what numbers go with what unit. Cosine 30 times -1 times your speed at 3 meters per second. So at the point we're moving at 3 meters per second, our frictional force is eating up energy at a rate of -32 watts. Oops. I guess I saw that one. I thought it was too low. There we go. There's the answer. So power can be a quick little equation, but sometimes you actually got to put some thinking into it in order to how to get the work.
Where does that cosine come from in the power equation?
This one or this one? Two cosines.
The one on top,
This guy?
yeah.
Oh, good. That's an easy one to explain. Okay, so you understand that guy. Good. It's the angle between, when you draw the work equation, work equals force times the displacement delta R times the angle, cosine of the angle between the direction the force is pointing and the direction the displacement is going. So for us, the frictional force goes up the ramp and the displacement goes down, and it's 180. The frictional force always works at 180 degrees away from your displacement. It never helps you out. It's always trying to rob you as fast as it can. Does that help you out?
Yeah, I think so.
Okay. Look back at the basic equation for work. This is where we're really, this is the start of chapter 7.
Okay, I'll look back at it.
Okay, but if you have any trouble, yeah, definitely. For friction, for frictional work, theta is always 180. Okay, so yeah, this one here is disconcerting to say the least, because this is the final and this is the initial. So typically we read left to right here in the US, so I would swap those babies. In physics we read left to right, so yeah, it looks confusing when you see that. My bad. So make sure this is the initial. Initially the springs are compressed, and then we let go of the mass and the springs snap back to equilibrium position. The question is, how much work is done by both springs? So the work by the springs net equals the work by spring 1 plus the work by spring 2. So you get off your old, brush off or dust off the old work or energy stored in the spring equation, which we covered on Friday. And this is negative K1 over 2 X. I'm going to call it delta X. We call it XA and XB, but let's make sure. Remember, this is how far it's stretched from equilibrium in each case. So this is delta X final 1 squared minus delta X initial 1 squared. And then you add in the work done from the second spring. And same equation, just with a subscript for 1 and 2. I'll swap out so we keep them kind of straight. There we go. So they end up at equilibrium position, back to equilibrium. So both of them have their final stretch or compression, if you want to call it, being 0. And wherever X naught can just be, here's X naught. So they all end up back at X naught. So they're stretched. Remember, all compressions and stretches are measured relative to X naught. As far as K1 and K2, we have, where's the magic words at? Both springs have a spring constant of 500 newtons per meter. So both Ks are the same in this case. As far as the stretch goes, or compression, we pull the mass to the right 0.2 meters. So one spring gets compressed 0.2 meters. At the same time, the other spring gets stretched by 0.2 meters. So in this case, the stretches and compressions are the same. So which one's which doesn't matter. Let's stick in a number here. And you go, what do I do if they're not the same? Well, you just keep track of this K1 goes with this stretch, let's say, okay? And he said, well, okay, the other spring, if this is the spring that got stretched and this is the spring that got compressed, so I put his K in there, the K's are the same, so it's easy in this today, but you have to keep the K with the right compression or stretch. That's all you gotta do. Maybe it was a poor choice. I thought it was a cool little problem to see with two springs, but maybe I should have made it a little bit, couldn't have done this problem any other way. Maybe I got a little bit too rambunctious or too ambitious here. But anyway, okay, so the other spring is K in here, and how far was he stretched from equilibrium or compressed? It was 0.2 again. And calculator. Somewhere. 0.2 squared. Equals 20 joules. So that's how much work the springs will do. And remember, if positive means the springs are doing work actually to move the mass, and if I figure out the work I did to do it, it'd be negative 20 joules because I don't do anything. You have to stretch the springs, it would have taken me positive work, and the springs would have done negative work. But when I get it all stretched or compressed and let go, the springs will do the work to get the mass back to equilibrium, so it'd be positive for me. So, that guy out there. Any question on that guy? No, nothing. Okay. Move on then to the power equation and power examples. How many joules of energy does a 100 watt light bulb use per hour? Okay, so power equals work expended over a delta T. That also equals, I think I call it just delta energy. Call it delta E, but I'll call it delta energy or delta T. So if you want to find power, you find out how much work it does in a certain amount of time or how much energy it uses up in a certain amount of time, or you can rearrange the equation and solve for the anything else in here. And we want to go for that energy. Delta energy equals power times time equals 100 watts times 1 hour. That's not a proper metric unit of time, so you do have to do a little conversion here, but you're going to see a lot of conversion when it comes to power. I can get away from it on exams, but just keep heads up, do extra problems. I mean, we usually don't leave light bulbs on for a few seconds. We leave them on for hours, maybe days. So you'll see some unusual time units that's being ready to convert over there. And there are 3,600 seconds in an hour. So 100 times 3,600 equals 100 equals 3.6 times 10 to the 5th. And if my remember a watt is a joule per second, so I'm just going to be left with joules. Okay. And to do number 7, how fast, which makes a lot more sense if you have number 6 here instead of number 5, because otherwise you'd have to do number 5 first. I don't even know if you'd get a right answer. 5, I'm sure, deals with another spring. How fast for the 70 kilogram person have to run to have the same kinetic energy that was calculated for energy found in the previous problem, number 6. So a person has so much energy, kinetic energy in this case, and that's going to be 1/2 mv squared. And we know how much energy they have. They have as much energy as this light bulb consumes in 1 hour's time. So we just saw for V. V equals 2 times 3.6 times 10 to the 5th over their mass, which is 70 kilograms. And this is a squared, so we have to take the square root. So person would be running at 101 meters per second. A little bit outside our realm of possibilities. It's about 10 times faster than a Olympic champion can run. So it's a little bit too fast. But nonetheless, if you want to, how fast would you have to be moving in order to spend that amount of energy? And that's how fast you'd be moving, how fast your kinetic energy, or if your kinetic energy was this, how fast would you be moving? And that's how quickly you'd be doing it. So light bulb uses a lot of energy in 1 hour. All right, not too much, but a lot for us. Any question on that guy? Otherwise, all right, we're gonna move on into the new stuff today then. And the new stuff is chapter 8. Three, that's 4. Chapter 8. Conservation of energy. And that is a pillar of physics. Also for biology and chemistry too, but I say a pillar, but they definitely utilize it. I mean, chemistry, reactions, endothermic, exothermic, I already mentioned that. They even get terms for it. And biology, I mean, that's, cell going to die, it's got to bring in energy. A lot of biology is just trying to figure out, transport of energy across the cell membrane. That's what makes life literally possible. So our goals for this chapter, it's a quick chapter, actually. It's a very important chapter, but it's extremely, I wish we had more time in this class, but the last 2 chapters we can cover actually are important topics, but fairly straightforward. We have potential energy, and it comes in 2 forms. The form we're going to talk about in just a few moments, gravitational. And the one we've already talked about is we make it look a little different. We give it a few different, because we're talking about energy versus work, but it's elastic energy, or AKA spring energy. So we've already talked about springs, which is why we did so. And then we have conservative versus non-conservative forces. What's the difference about those guys? And then conservation of mechanical energy, which is really just a stepping stone for the big guy, conservation of total energy. That's a big guy. All right. So. So, go back to what I just said. The first guy we're going to talk about, gravitational potential energy. Okay, so we'd like an equation. Well, I mean, we need an equation. I guess you should say what's potential energy. Potential energy equals stored energy. That's how it's going to lead back to springs. You compress a spring and you hold it back, or you cock it somehow, like with maybe a dart gun, and you let go of it, but you still keep the spring cocked. That spring's got energy in it, and we all know that. When you press the trigger or you release it, the mass or whatever is at the end of the spring, or the end of the spring just itself, will spring back. So there's energy in the system that has potential to do work, and that's what potential energy is. It's stored energy which can potentially do work for you. That's why we go to all problem, make a little dart gun. Also, as far as springs, that makes obvious. This explains why hydroelectric dams. Why do they make hydroelectric dams? What are they trying to get out of it? A lot of work for it. What do you get out of a hydroelectric dam? Like Hoover Dam. Miss Zuma, you got an idea? What's those big dams used for? Electricity. The electric part, yeah, electricity. They make electricity. Via stored gravitational energy. I mean, highly controversial to put dams on rivers. It clogs them up. It prevents natural flow. Fish have a hard, if not impossible, time to use the river as they normally would. So there's all kinds of environmentalists which will descend upon a dam. Like this is, you're destroying the environment. But okay, that's true. You're altering the environment, and you could be destroying if you're not careful. But everybody wants electricity. We all want to run our little cell phones and our iPads and our toasters and our heaters when it gets cold outside. AC when it gets cold, too warm. So this is one way we make electricity without any pollution. I mean, this is and what we do is we build a gigantic, get this valley down here with a river. You put a dam across it, and behind it is all this water, and that water is trying to get out, and we make the water come out through these little turbines down here. And when the water goes through the turbines, they push the turbines, rotate the turbines. You'll find this out in the second semester in Physics 175. When you move a coil of wire in the presence of a magnet, you get magic. You get electricity. It's amazing it works out like that. So we dam up a river really high so that when something falls, the water goes, we force it out the bottom. That high potential energy of the water at the top will cause that giant turbine or a set of turbines to turn at the bottom. So let's talk about that. Let's get an equation that discusses the potential energy for gravity. We've had one already before for the springs, a little bit of tinkering. I'll get it exactly. Actually, it's just window dressing. Goes through one now for gravity. So let's consider another piece of paper. Consider a mass M. I'm gonna do a little bit of derivation here. I always kind of wonder if I should do them, but I'll show you where it comes from, because the equation is actually very simplistic. And a lot of you, if anybody's had physics before, you've had this equation coming up about gravitational potential energy. Consider a mass M that moves a tiny distance dl under the gravitational force Fg. So here's a little mass. Ooh, those straight lines. Here's gravity trying to pull it down. And meanwhile, the mass, though, even though the gravity's pulling it down, the mass is moving over here. And you think, well, it will never move up. You're right. But we see that when we deal with springs, springs will never stretch themselves. They would do negative work. I would have to do that. But when the spring is let go, it will try to bring itself back to equilibrium. So yes, gravity won't ever make an object go up, but that'll just be, we'll find out that'll be negative work for it. You know, that means I've got to do some work for it too. But anyway, the equation will be you know, interchangeable. So there's an angle theta between the gravitational force and dl, and you can see where we did work first. I mean, this is starting to set us up to do a work equation, and work has energy in it, or deals with energy. There's my axes, positive x, positive y. And so the question becomes, how much work does gravity do to move m a distance dl? And well, we're going to use the work equation, but technically we're moving it just a little bitty distance. So we're only going to get a little bit of work out. You might think, why don't I call it a delta L? You would be okay with calling it a delta L, but I'm really, if you had any kind of calculus, and you've seen me with calculus over integration, I'm sneaking up on an integral again. That's how I got the elastic one for the spring. That's how I got the spring energy. I got an equation for the you know, the Hooke's law, and I stuck it in the work equation. I said, let's add up all these little bitty pieces of work because the force could change, and then I add them all together in calculus. It's called integration. So some if the transition is smooth. So I'm just going to do the same way here. So the work, Gene's looking like this there. The work done by the gravitational energy is going to equal the force times dl, that's the distance traveled, times cosine theta. That's vaguely familiar from the, I said, well, it looks like the derivation I did on Friday or whenever, Friday. And this also, even before that, kind of looks like the work equation, which it is the work equation. It's applied for small distances. So work equals force, distance, cosine theta between the two, between the force and the displacement. That's how much work for a little change in position. I like to know the whole thing. So I want the total work done by Fg to move m from a point, let's just call it A, to B. And where dl is a little piece of this path. Right. So now I'm doing this. I'm starting at A, and I'm going to end up at B. Follow some weird path. Okay. And I think, well, that'd be a horrible path to try to describe mathematically, and you would be right. We're going to find out the magic of a conservative force coming up. So here I am along, I'm going to add up all the little works. I'm going to add up the work it takes to move to this spot, and the work it takes to skip this spot, and this spot, and this spot. I'm just going to keep adding up the work, and then I'm going to, sum them all together. It's like if I can move it, just a little part of a time. Today, I'll move it from here to here. Ooh, how much work did that take? I'm going to take a rest now. Tomorrow or maybe this afternoon, I'll move from here to here. How much work did that take? Ooh, okay, I'm tired. Tonight, I'll do a little bit more. And at the end of the day, I'll add up all the work I did, or however long it takes me to go from A to B. Of course, we're just smoothly going to do it, but that helps you buy this argument about these little pieces adding up. And the good thing is, it is work scalars, so scalar things we can add up without having to worry about vectors here, at least overall. So you figure out how much work it would take you to move over a little bit of DL, there's a little bit of piece there, a little bitty piece of this DL right there. And okay, you'd have to do a work calculation. And for this part, the theta would be constant. But as I move along this curve, my theta is going to be starting to change. See, on last week's on the Friday derivation for the spring, the force was always changing because Hooke's law is not constant. In this case, the force is constant, m times g, but the angle is changing. So we still got a little bit of a problem here. This guy, here's your path. M moves from A to B. It's going to keep adding up those little bit of, every little piece of DL will be associated with it, will be a piece of work. Define total work. Done by FG. Well, let's call it W net work, or if you like to call it tot for total, that's fine. This would be the work that happens when I move along DL, this little bitty piece. And I add up the work along DL2, which I guess I shouldn't have called it DL2, because you think, what happened in between? There's all kinds of little DLs in between. I just drew them far apart so you can see that, I didn't get the angles. And you just keep doing that. Like I said, it's just like you're picking up breadcrumbs, and all along the way at the end, how much breadcrumbs did I pick up? How much work did I actually do? And the math guys would say, well, this is summation, but if the angle is smoothly changing, which it will, it's not going to abruptly change, or else you're pointing in another direction. It's just smoothly, this theta smoothly leads into theta 2. It's like going down a hill on a roller coaster. We do an integral. We go from A to B, FG, DL, cosine theta. Yeah, I love integration. I mean, it's just, you guys teach, or you learn this hopefully in math class, and think, what am I using it for? Well, with physics, we drag this out all the time. Now, this is great. Let me do an integral here, and I can get a nice equation. So like it's in the case on Friday, I'm going to use an integration here. I'm going to use integrals, but at the end, I'm going to get this nice, simple equation that literally I used in high school. It was one of the first equation I had in physics way back in high school. And Mr. Barron didn't show us where it derived. It made sense. He didn't show the derivation because we had no calculus at the time, but we're just using this to show you where the equation comes from. The force, though, is from the gravitational force, is just your weight equation. It's m times g. And provided g is constant, or let's just say mg is constant. In other words, your mass doesn't, you don't lose any mass, you don't gain any mass. And also g, I gotta admit, now if we're launching to the moon, acceleration of gravity is not constant, but if we're near the surface and moving things up and down a few meters, if you move it up and down hundreds of meters, and you wouldn't be able to calculate the difference in g. But technically, if you had a good enough piece of apparatus, you would actually find out that g would vary. But in everyday life, we don't worry about that. Airplanes do not have to suddenly work at, oh no, you're going to fly at 30,000 feet. Oh, you're going to need more gasoline because more fuel because acceleration of gravity is a little bit different. It's minuscule difference for us on at that level. So you factor out what's constant, standard name of the game is an integral. And but you're left with a little bit of a quandary. Unlike on Friday when I had an integral that had just an x dx in it, and that was easy. This is a little bit of a problem because I'm integrating over dl. But theta is changing too. So I need I've got a problem with that. It's like solving an equation, let's say, and this isn't solving exactly the equation, but let's say we're solving an equation, it was 2x equals 4. I can do that. Okay, x is my unknown. I divide out by 2, I get x equals 2. But let's say it was 2x times y equals 4, and I have to solve for x now. And I can't do that. I don't know what y is. Y is an unknown. I can solve x in terms of y, but without knowing y, I'm in trouble. I can't find an actual numerical number. Unless, and you need somebody to say, well, if that happens, you just need a second equation. You need another equation relating x and y together. You get 2 equations, 2 unknowns, and you're all set. All goes well. And that's what I need here. I need a relationship between theta and dl. Just like if you had an equation with x plus y, let's just make it pluses, x plus y equals 10. There's got to be another equation out there to solve it. If you want to solve it, if you have any hope of solving the equation, you've got to be either told what y is, directed y equals 5, or you can actually have another equation, let's say 2x plus 3y equals something or other. And you solve for one, you stick it in there, and off you go to the races. So that's what I'm going to show here. Here's my mass. There's dl. There's mg, my gravitational force. And here's theta. Oh, I could do this. Remember, this was positive x and positive y. I want to move along dl. We go from here. This mass goes from here up to this tip of this arrow. Then it moves a distance dl, a little bit dl. If you just want to call it dl, it's fine. But this is also equivalent to sliding so far along the x direction, dx. And this is moving so far along the y direction, dy. So this is the hypotenuse of a triangle, and I showed you the sides of it. And just for the fun of it, let's call this angle right here phi, angle phi. So we got theta and then phi. And phi we wouldn't even thought twice about because it's not the angle we want when we deal with work, but it is an angle we can use. By the drawing, cosine phi equals adjacent, always does, dy over dl. Remember that. Up here with an arrow means it's dl pointing in this direction, but it just has magnitude dl. But also, by the drawing, ironic, I got this derivative, this rule here because my son just went through this. As I've told everybody, I think all the class he had a geometry test last week in high school. You have a linear angle here. Well, that's the name of it. Theta plus phi equals 180 degrees. So theta equals 180 minus phi. Here comes the thing I always have to either get a calculator out or look in the front of a book or grab my CRC handbook or something like that. Thing that I always appreciated, but it was always hard to remember them all. There's things, I know you guys have seen these, by trig identities, by a trig identity, cosine theta, and you think, why are we doing that? We're having trouble So DL and cosine. I need another equation to get one of them in terms of the other guy. It's cosine theta. So by a trig identity, cosine theta equals cosine of 180 minus the supplement, which is phi, and that equals negative cosine phi. So if I wanted to, I can go back up here and I can swap cosine theta and cosine phi. And you say, well, you've gained nothing because you've just got a different angle there. That's right, but I got this formula right here. As dy over dl equals cosine phi, and cosine phi equals negative cosine theta, dy equals negative cosine theta, or dy equals negative dl cosine theta. If I want to, I can just say one more thing. Negative dy equals dl cosine theta. You got that? I'm gonna slide this other paper underneath it. Look at that. I can take dl cosine theta, which has two variables in it, and I can just plug in negative dy in place of all this stuff here. Matter of fact, let me watch one body do. I'm probably say this is my equation A. I'm going to plug into A. So W net equals mg going from A to B of just negative dy. Factor out the negative sign. That becomes an integral that's even easier now than Friday. I did a lot of work here and sometimes life physics doesn't give you strawberries or lemonade, it gives you lemons. But here with a trig identity and a relationship geometrically, I'm able to get rid of my two equations or two variables, theta and dl. And I didn't get one in terms of the other. I completely swapped them both out for a dy. And this is an easier integral than last week. I can integrate this once I do all this work. The integral of dy equals negative mg, just plain y. And when it goes from A to B, since we're integrating over y, this would be y initial to y final. Or if you want to, this equals y at point A, and that equals the y value at point B. We always usually say initial to final. And we finally get, we can evaluate that. W net equals negative mg, and y final minus y initial is better known as a, there you go, should all wait for, thanks very much. Monday morning, it's hard to keep focused, that's right, delta y. And this is the work done by the gravitational force. Remember when it came to springs, if we stretched, if the spring got stretched from equilibrium, it was negative work. Spring doesn't want to do that. It will do, and that it's common sense. We know a spring that's just not stretched, it's just going to sit there forever. If you want to stretch it, you got to do it. You want to compress it, you got to do it. But once it's compressed, once it's stretched, it's not magic for that. If you let go of it, the spring springs back to its equilibrium position. We know the spring's going to do that. We've known that ever since, age 2. You you're surprised for the first slinky you saw or something like that. After that, the excitement was over. We just knew the spring would go back to its normal position, and it was moving, but we knew it would do that. when it comes to an object laying on the ground, will it just magically rise up? No, it won't. I mean, it won't do that. We would be very worried or very frightened or mystified by why suddenly does an object start rising off the ground if it doesn't look like it's got helium in it or a rocket pack or something like that strapped to it. We'd be kind of scared. What's going on? On the other hand, if we had an object, so work done by the gravitational force there is negative. If y final is greater than y initial, delta y is positive. So work net by the gravitational force is less than 0. And that means gravity's not going to do it for it. The object will stay on the ground forever. It will not rise. If you say, well, how long is it going to take for that thing to rise? It will take forever because gravity's not going to do it. You're going to have to do it. You're going to have to reach down there and grab the object and lift it up. On the other hand, if you have an object lifted up off the ground, you're holding on to it, and you drop it, you let go of it. Well, delta y is now less than 0. So the net work by the gravitational force is positive. And then gravity will do the work for you. So if you let go of an object, it will fall. And we don't think that's magical. We say, oh, gravity did that for me. Gravity did that. Yeah, sure. It did positive work. So we have a work equation for the gravitational. It's not quite the same as same potential energy, but we're very, very close to that. Let's see. I got like 14 minutes. Yeah, I can do it. Show the video, but I can tack the video onto the lecture that I make available online. All right. So the neat observation. I'm sure on a Monday you're all up for the neat observation here. It may be very seen, or maybe it's escaped because it's Monday. I started off with a very too funky. But the path going from A to B was this curved path thing. I don't know. I didn't describe it. It could be. I've never math and calculus with you we had to make an equation to describe a path. I think it quite lengthy. I mean, it depends on how the path, how smooth it is. But at the end of that, I didn't even worry about the path. If you notice, the only thing I worried about was what the change in the height was, the y. I didn't care anything about x or z or how it got to y. I just knew it went from y initial to y final with no regard to the path. So in other words, it was independent of the path. Work done by gravity only depends on the endpoints. Hurrah! I mean, that's great. I mean, could you imagine if we had to worry about that crazy path they just drew? I mean, you'd be completely handcuffed. You wouldn't be able to do anything until you had a really ugly mathematical equation, perhaps. But this guy here, it doesn't matter. Just depends upon the endpoints, specifically endpoints for y, and not the path. So in other words, if I have positive 1, I'm just going to draw something here, and this over here is positive x. So this guy here is y initial, and over here is y final. So I should draw the line first. Path number 1. So path number 1, you go from y initial to y final. And you do something in the x, but I just care about that and the y. And here's path number 2. You're all over the place. There, that's path 2. Could you imagine trying to get a mathematical formula for that crazy curve? I mean, no, you couldn't do it. I mean, yeah, you could with a great computer, you can figure it out. But prior to 1980, 1970s, you'd be, that's it, game over, unless you get some kind of You'd have to do some approximation or stuff like that. But the neat thing is, the work done by FG, gravity, not total work from any other forces. So present, that might be present. Along path number 1 equals work done by the gravitational force along path number 2. Okay. And that resembles closely the work done by the spring. Work S equals, I mean, the format looks a little bit different as far as, oh, I see a square here, but it just depends upon where I started from and where I ended up. I could have taken that spring, I have my spring with me, walked away, but I could take that spring, back, forth, back, forth, back, forth, back, forth. When I stretch it, I'm doing work. When the spring comes back, the spring's doing the work. It's doing positive work, negative work, positive work, positive. But it doesn't care. I get work back out. I take work, I put work in. It just depends on where I finally stop. And that's it. Okay, I didn't make that really clear. We just stretch the spring, but if we let it compress and stretch it right back out, I'd get energy in and I'd pull energy back out of it. So. Terms like this, which depend only upon endpoints, when a force does work that only depends on its start and final endpoints. In other words, to say it's path independent. We call such a force conservative. And examples of conservative forces will be the elastic, spring force. That's why our equation worked the way it did. I mean, it is for an ideal spring, but it works out. The gravitational force. Think of me in 175. Thing called the Coulomb force. Deals with electrostatics, or electrodynamics too, but it's the force of attraction or repulsion between two like or unlike charges and signs. Also, I guess the nuclear force too. We're not going to get that. So it's just, etc. There are a few forces other than that. So these are really cool things because we can derive. It may be hard to derive the equation a little bit, but once you get the equation, boom, the only thing it depends upon is where do I start, where do I end? That's all you got. And even though the derivation may be a little bit above the pay grade of most high school students or some high school students, the end result equations like that you can do in, I think you can do in 5th grade. I don't know, somewhere around there where as soon as you can do powers. A non-conservative force does work that depends upon the entire path. Anybody know an example of a force that depends upon the path and determine how much work it does? The big guy. You're trying to move something, you try to do it in the shortest amount of the time or shortest path possible, usually because you don't want to avoid work robbed from you by what? It deals with total work. But when you start moving something, what robs you of energy? What force robs you? Friction. You trying to move a big refrigerator? You go, unless there's something between, something in the way, you move from here to there along path 1. You're insane to do the red thing. We know why. Well, you're just, I mean, friction is robbing you of energy along the entire path. And so, yeah, you can do it from all this stuff, but you're going to put in a heck of a lot of work because friction is just going to sit there, and as soon as you start moving, it's going to take the energy back out once it stops the object, or even doesn't want to start it from moving to begin with. So, and you got a day to kill. You don't want to go outside this nice November weather. Do path 2. I would do path 1. Get the work done. And do it all in line. I didn't know if I'd get there now. I'm going to get there. Woo-hoo. 4 minutes, 5 minutes. Good enough. Now, I've just been dealing with, still dealing with work. I said I'd get an equation for this thing called potential energy. I better spell it correctly. Potential energy. Recall what I just said. Work done by the gravitational force is Wg equals negative mg delta y. To cause an object to rise, y final is greater than y initial with no acceleration. Okay, so I mean, we're going to be talking about energy here. So obviously, I shouldn't say obviously, but you can imagine that the faster you raise something, boy, it's going to take a lot more energy. I mean, that's why we have jet airplanes. I mean, you know, I can climb, if the ladder is big enough, I can climb to 30,000 feet, but to get all those people up there really, really fast, all that weight, boy, that's a big acceleration. And that's going to require a lot of fuel. Okay, so you can do the same thing with balloons, but you're not going to be able to accelerate that fast. So the cause of an object to rise with no acceleration. So I'm just saying there's not like excess energy is not going into making this object move fast. You're just trying to get it there. Needs an external force which is equal to Fg in magnitude. In other words, Fg equals F exterior, or if you want to put this in terms of vectors, F exterior, X external equals negative the gravitational force. Now, this is going to be you. You want to raise something up, you've got to overcome the gravitational force, or at least neutralize it. Right? If you're bigger than the gravitational force, you're going to raise it. You're going to start accelerating it. The bigger the external force, the faster you can get it up there. But you've got to at least overcome gravity, and this is our make or break point. Just trying to overcome gravity. I could go back and redo the entire calculation I just did. I just stick in a negative sign for Fg. If I redid the calculation for an external force equal to negative Fg, so I just stick a negative sign in every place I had that mg, I'd put negative mg. I'd find that the external work equals, oops, not negative anymore, mg delta y. So I'd get the same thing without the negative sign. Look familiar, I hope. That's what I did with the spring. I had a work done by the spring. It was negative k over 2, and the quantity with the x final squared minus x initial squared. And I said, well, the work external is going to be opposite that. And so I just had the same equation and I just swapped it. we define gravitational potential energy to be a U sub G. And we, seriously, I'll find another paper. I got another paper just to go another piece of paper. Okay. Change in gravitational potential energy equals delta UG, and delta UG equals energy delta Y. Where delta Y equals is always a final minus initial. Then with this, the springs, I'm out of time, but I similarly by the springs, delta U springs equals 1/2 K x final squared minus x initial squared. Ding. And that ends it. We have two new equations for energy. Our first one's really